Oil filter is a vital component in car engine that ensures the vehicle to run smoothly for many miles. Over time, contaminants in the engine oil build up inside the oil filter, clogging it and making it less effective. Because of this, oil filters must be changed regularly. If you go to a mechanic for an oil change, there is a risk that this mechanic will charge higher prices for cheap oil, which could possibly damage your engine. It is more secure to change the oil by ourselves. However, the oil filter must be tightened very hard to prevent leakage, making it very difficult to be removed. And sometimes the surface of the oil filter can be slippery because of the oil. In order to solve all these problems, our group decided to design a tool that could remove the oil filter easily and effectively. This tool will work on oil filter of various sizes in various angles.
In order to design our oil filter wrench, we must first create a framework to determine all the functions of our tool. These functions will ensure that our oil filter wrench operates as desired. First, the tool must be able to fit around the housing of a typical oil filter that is commonly used in modern cars. The wrench must be able to hold and grip the surface of the oil filter canisters, even if they are oily. In the process of gripping the oil filter, it would be beneficial if it did not cause significant damage to the housing, as this can cause oil to leak out. To make the tool more versatile for the user must be able to apply torque at any angle relative to the gripped location. This will allow the user to approach the oil filter at any angle. Finally, the tool must be comfortable for the user to operate. To do this, it must be both ergonomically comfortable to hold in the hand while also being lightweight so it does not cause strain on the arm. Throughout the duration of the project, we had to create written reports that showed the progress that was being made on our project. The first step was to create a Gantt chart. The Gantt chart is a tabulated schedule that shows the due dates for each assignment and gives information on how much time we have to do each of them. Next, the project specification. This report provides a framework for the design of our wrench, the parameters under which it must follow, and the goals it must achieve. The prototype concept details the physical design of our wrench and the method that will be used to test it and determine if it works. The prototype drawing is a CAD drawing of our prototype that informs the exact dimensions of our product. For the materials and components list, we decided that we will fabricate the handles and jaw from scratch while purchasing all the bolts and nuts since they are standard parts. The design review is a recap of all the previous assignments. Finally, the economic and environmental report details the cost of mass producing our tool and the environmental impacts it will have from its fabrication, use, and disposal. The final report compiles and summarizes all of the previous reports that were handed in. To inform us of our design choices, we gathered information from a variety of sources. First, we found 2 textbooks that were useful for learning about the physical properties of our tool. These texts were Shigley's Mechanical Engineering and Materials Science and Engineering, an Introduction. From these textbooks, we found information regarding yield strength and ultimate tensile strength. The American Society for Testing and Materials provides accurate data on these values for a variety of materials. Based on our estimates and calculations, we decided that it was best to make the tool entirely out of metal. Since this tool will be used many of thousands of times by mechanics, it will also undergo cyclical loading and suffer from fatigue stress. To prevent the corrosion of our product, we chose metals that were naturally corrosion resistant and similar in location on the galvanic series. Since the tool is designed like a wrench, it has hinges and will require non-permanent fasteners, since some maintenance will have to be performed on it throughout its lifetime of use. Finally, the durability of our tool will be determined using finite element analysis. This will inform us if the tool is either not strong enough or has excess material and can be slimmed down to reduce material costs.
For the technology review, we did a pattern search. Here are 3 of our samples. We have listed out the strong points and shortcomings. For the first one at the left, it's adaptable to multiple sizes of filters. It's tightened the more you turn. It would not damage the oil filter and allows limited space operations. The downside of it is that the tool can have possible slippage and it requires a ratchet to operate. For the middle one, it's able to provide strong grip in oily surface. It requires less space to operate due to the rotating jaws, and it's adaptable to multiple sizes of oil filters. The downside of it is that it could damage the oil filter housing. The one at the right can also provide good gripping powers in oily surface. However, it's limited to a small range of sizes and it requires a ratchet to operate. Lastly, it can also damage the oil filter housing. We gather the advantages of these patterns to insert them into our design, and we try to avoid these shortcomings.
We created 2 surveys on automotive forums on Reddit. One is about methods used to remove the oil filter and the satisfaction with the tool, and the other survey is about the difficulties throughout the process. 250 people take these surveys, and 200 of them are mechanics or automotive professionals. The pictures of word cloud is shown in the slide, and we can find that the most common removal methods are screwdriver puncture and ratchet tools. And the biggest issue is filters are over-tightened. We did a functional decomposition, and 2 sub-functions and 2 auxiliary functions were identified for the overall function of removing an oil filter. Different combinations from each form of each function can be evaluated to create the morphological designs. With so many possible combinations, we used engineering judgment while keeping customer needs in mind, like ergonomics and economics, to eliminate undesirable combinations. The designs are generated using the morphological matrix, and brainstorming are filtered to find the overall best designs in concept selection. 27 designs were generated, and 10 best design concepts were then passed along to the objective selection method. To screen the choices, the best 10 designs were screened to 5 by going through a screening matrix, which quantitatively screens the design based on a number of characteristics relative to a reference design. And the last 5 designs are selected by continuing on to be scored against the same characteristics but out of a maximum score, with each characteristics being weighted out of 100%. The concept selection process is shown in the slide, and the selected design is M7 hinged filter wrench. Then the chosen design can be modeled.
Here's our design solution. The sharp T at the end of the handles can provide strong grip to our oil filter and can operate in different angles. The design dimensions of our design can help our tool to operate in crowded space and to clamp different sizes of oil filters. Besides that, the use of a 6061 aluminum alloy can help us reduce the weight of the tool. Finally, the removable vice screw handle can help provide gripping powers. Here's the FEA of our design, which is done in SolidWorks. We have chosen the handle of our design because it's taking and transferring most of the forces from our hand to the oil filter, which means it's the most important component of our design. We simulated the situation based on our experience on oil change. 30 pounds of force and pressure has been applied on the holding surface and the contact surface between the T and the handle. And we chose the material of 6061 aluminum alloy. At the end, we obtained a maximum stress of 1483 psi and a minimum stress of 0.2145 psi. For the displacement, we obtained a maximum of 2.092 times 10 to the negative 4 inches and a minimum of 3.937 times 10 to the negative 32 inches. Anyway, our factor of safety is always greater than 4. And one thing to notice is that the deformation scale of this FEA is 5,800. That's why it looks exaggerated.
A good analysis that can be performed on our tool is mechanical advantage analysis. This provides a relationship between the work, force, and/or the distance between the input and the output. Our input is the rotation of the vice screw handle, and the output is the movement of the spikes. Since the vice screw moves 1/20th of an inch in the axis of rotation for every rotation, and the handle that turns it rotates with a circumference of 28.26 inches, the power transmission is given in equation 2 and is shown to be 565.2. Now, as the ratio of the lengths between the vice screw and the center of rotation of the tool, and the spikes in the center of rotation of the tool is 1.4, that also amplifies the power transmission. As shown in equation 3, this is approximately 800. That is, for every 1 newton of force or distance traveled at the handle, 800 newtons of force, or 800 times that distance traveled at the handle, occurs at the spikes. This allows for quite a bit of mechanical advantage and would allow for puncturing of any sorts of metal to be very easy. An economic analysis was performed on our tool to establish the validity of a 1,000-part production run. First, on the left in the table, you could see the price for what per part for 1,000 tools would cost. This only comes to about $4.48 per tool, or $4,482 for the whole 1,000-part production run. Now, the engineering analysis for our tool would probably only take one engineer half of a week, and you could see our estimates for the cost of that on the right. The total cost for the engineering would amount to $1.32. Now, that, when combined with the total cost to produce one tool, only brings the total to about $6, which is very reasonable. The analysis for the machining times and costs are given here in the table. As you can see, the total time to complete one part of the tool is approximately 9 minutes, with an assembly cost of about 30 cents per tool, as it only takes 1.5 minutes to assemble. This brings our total cost per tool to about $15.55. Many of these parts would need to be made on a 4 to 6 axis CNC machine to compete with these amount of times. That is, those machines can change tools rapidly, do many operations per minute, and it would be the only way to produce it with these times, which is accounted for in the rather steep $100 per hour fabrication rate. Combining the cost to machine, the engineering cost, and the materials cost from the last slide, the total cost per tool comes down to $21.35, which puts us just under our recommended asking price of $25 per tool. Now, this is only for a very small production run of 1,000 parts, and this price could be greatly reduced if you increase the amount of parts produced. But for our analysis, this seems more than reasonable.
A prototype for our design is successfully fabricated. The handles were cut from an aluminum plate. The spikes were made by steel. The prototype and the CAD model have a very good match. Most specs on the drawings were followed on the prototype. The dimension is also expected and is very user-friendly. The machining took place in the machine shop in Jarvis Hall after the CAD model was produced. We spent different days on making this prototype, but the total time that we spent on the fabrication process is about 5 hours. The speed could be improved if we want to make a second or a third prototype. Unfortunately, one of the handle was accidentally cut off by one of our group members, but we fixed it by reattaching it using bolts and nuts, giving it the same strength like it was never been cut before. The spikes are super glued onto the handles, making it very secure and strong. We also refined the edges on the prototype, so when someone is using it, the person won't get his hand cut. The finish on this prototype is very good and is production ready, and it is fully ready for testing. Our oil filter removal tool obtains a successful result on the testing. The tool can puncture a filter housing to maintain grip in any condition without the effort of using a hammer or a screwdriver. The large shear area at the spike to the filter makes tearing and slippery very unlikely to happen. It can also torque at any relative angle as expected. The tool was able to overcome the over-tightening that was used in the experimental test. Even though little deflection occurred in tool, the tool still maintains the 791 to 1 force advantage most of the time. Based on the success of the prototype and the profitable manufacturability shown in the economic analysis, the production of this tool may be viable if there is a significant market demand. Our group would like to call this project successful, and thank you for your time.